Have you ever wondered what makes a quantum computer quantum? It's a fascinating question that takes us deep into the realms of physics and computer science. Unlike classical computers, which operate using bits, quantum computers use quantum bits or qubits. This fundamental shift allows them to process information in entirely new ways, opening up a world of possibilities. But what does quantum really mean in this context? Quantum computing, as the name suggests, revolves around the principles of quantum mechanics, which we'll delve into next. Quantum mechanics sounds complicated, right? But what if we simplify it? First, let's start with the basics. Quantum mechanics is a branch of physics that deals with phenomena on a very small scale, like molecules, atoms, and subatomic particles. It's a world where the rules of classical physics that we're used to no longer apply. One of the key principles of quantum mechanics is the concept of superposition. Superposition is like being in two places at once. Imagine you're at home and at school at the same time. Sounds impossible, right? But in the quantum world, particles can exist in multiple states at once. A particle in a state of superposition can be both spinning clockwise and counterclockwise simultaneously. Now, let's move on to entanglement. It's a bit like the ultimate long-distance relationship. Two particles become entangled when they interact in a certain way. After they're entangled, the state of one particle will instantly affect the state of the other, no matter how far apart they are. If one particle is spinning clockwise, the other will be spinning counterclockwise, even if they're on opposite sides of the universe. This is what Albert Einstein famously called spooky action at a distance. But what does all this have to do with computing? Well, in traditional computing, data is processed in bits, which can be either 0 or 1. But in quantum computing, data is processed in quantum bits or qubits, which thanks to superposition, can be 0 and 1 at the same time. This allows quantum computers to process information much faster and solve complex problems that are beyond the reach of traditional computers. Entanglement, on the other hand, allows qubits that are far apart to work together instantly, leading to even more computing possibilities. So in essence, quantum mechanics allows particles to exist in multiple states at once and to link together no matter how far apart, leading to some pretty incredible computing possibilities. Now that we understand a bit about quantum mechanics, how does a quantum computer use these principles? Well, while your everyday classical computer operates using bits, a quantum computer marches to the beat of a different drum, utilizing what we call qubits. Qubits, or quantum bits, are the fundamental units of information in quantum computing. What makes qubits so special? It's all about their quantum nature. In a classical computer, a bit can either be a 0 or a 1. It's an either-or situation, but a qubit, thanks to the principle of superposition, can be in a state where it is both 0 and 1 at the same time. Imagine being able to be in two places at once. That's what a qubit can do, at least metaphorically speaking. But that's not all. There's another principle in quantum mechanics called entanglement. When two qubits become entangled, the state of one qubit is directly connected to the state of the other, no matter how far apart they are. This eerie connection allows for a higher degree of complexity in computations, as the state of one qubit can affect the state of another. And what are the implications of these quantum quirks? Speed and power. A quantum computer, thanks to these superpositioned and entangled qubits, can process vast amounts of data simultaneously. It can perform many calculations at once, rather than sequentially like a classical computer. This means a quantum computer could potentially solve complex problems, like factoring large numbers or simulating the behavior of molecules, much faster than any classical computer ever could. So why does this matter? Well, it opens up new possibilities in fields like cryptography, drug discovery, weather forecasting, and even artificial intelligence. The potential applications are as vast as the quantum world itself, so a quantum computer could potentially solve problems in seconds that would take a classical computer millions of years. Quantum computing, then, holds the promise of a revolution in how we process information and tackle complex problems. The quantum age is upon us, and it's a fascinating time to be alive. Scene script. Sounds fantastic, doesn't it? But what are the challenges in making quantum computing a reality? Well, let's start with the technical issues. Quantum computing relies on a delicate state of matter known as superposition. This allows quantum bits, or qubits, to exist in multiple states simultaneously, vastly increasing their computational power. But maintaining this superposition is no easy task. The slightest interference from the outside environment can cause qubits to lose their quantum state in a process known as decoherence. This makes quantum computers incredibly sensitive and difficult to build, requiring ultra-cold temperatures and isolated environments. Then there's the question of error correction. You see, in classical computing, if a bit flips from 0 to 1 due to some error, it's relatively straightforward to identify and correct. But in quantum computing, things are less clear-cut. Because qubits can be in multiple states at once, errors can be much harder to detect, let alone correct. Researchers are working hard to develop quantum error correction techniques, but it's a significant challenge. But the challenges of quantum computing don't stop at the technical. There are societal implications to consider as well. Take data security, for instance. Today's encryption systems rely on complex mathematical problems that even the fastest supercomputers can't solve quickly. But a sufficiently powerful quantum computer could crack these codes with ease, rendering our current security measures obsolete. This poses a real threat to data security and privacy, and it's a challenge we'll have to address as quantum computing advances. And let's not forget the educational challenge. Quantum mechanics is famously complex and counterintuitive. Training a new generation of quantum engineers and scientists will require a significant investment in education and resources. Indeed, the road to practical quantum computing is filled with hurdles, but the potential rewards make it a journey worth undertaking. After all, the promise of quantum computing is immense. It could revolutionize fields from medicine to climate science, opening up new possibilities we can barely imagine. The challenges are steep, but so are the potential rewards. So, what does the future hold for quantum computing? Well, it's a question that sparks the imagination, isn't it? Quantum computing, with its potential to process complex calculations at lightning speeds, is an exciting frontier in technology. But where could this take us? Let's start with medicine. Researchers believe that quantum computers could revolutionize drug discovery. By simulating the behavior of molecules at quantum level, scientists could quickly and accurately predict the effects of potential drugs, speeding up the development process and saving precious time in the fight against diseases. And what about cryptography? Today's encryption methods might not stand a chance against the power of quantum computing. But fear not, for the same technology that could break codes can also create them. Quantum cryptography could bring about a new era of ultra-secure communication, keeping our data safe in a world where information is gold. Now, let's turn to climate modeling. The complexity of our planet's climate is a challenge for classical computers. But quantum computers, with their ability to handle multiple variables at once, could provide us with more accurate climate predictions. This could be instrumental in our ongoing battle against climate change, helping us to develop effective strategies for a sustainable future. Of course, we're not there yet. Quantum computing is a field of ongoing research, and there's still much to learn. But progress is being made every day. Scientists and engineers around the world are working tirelessly to overcome the challenges and unlock the full potential of this technology. Quantum computing is not just about faster processing, it's about tackling problems that were previously thought to be insurmountable. It's about pushing the boundaries of what we know and what we can achieve. While the quantum future may seem like the stuff of science fiction, it's closer to reality than you might think. Let's quickly recap what we've learned about quantum computing. We started with the basis of it all, the principles of quantum mechanics. These principles, like superposition and entanglement, form the backbone of quantum computing. Superposition allows quantum bits, or qubits, to exist in multiple states at once, unlike conventional bits that can only be in one state. Entanglement, on the other hand, links qubits in such a way that the state of one can instantly affect the state of another, regardless of the distance between them. Next, we dove into the workings of a quantum computer. We saw how these machines use qubits to process information, providing potentially exponential computational power compared to classical computers. A single quantum computer could potentially outperform the world's most powerful supercomputers in solving certain complex problems. However, building these quantum computers is no easy feat. We discussed the challenges faced, such as maintaining quantum coherence and minimizing quantum errors. These are significant hurdles to overcome, but they're not insurmountable. Finally, we envisioned the future of quantum computing. We looked at the potential applications, from cryptography to drug discovery, and how they could revolutionize various industries. So that's quantum computing in a nutshell. A fascinating blend of science, technology, and potential that could revolutionize our world.